Hello, Hello, this is video number 4 on chapter 11, and we will be talking about the strengths of acids and bases. How to tell if the acid you have is strong or weak. Mm, so the strength of the acid depends on how the acid is dissociating in water. So for example, this HCl, we know that HCl is very strong acid. And when we check the dissociation in water, you can see that it is completely dissociated. And you look here, so this is HCl here, and you put it in water, and it will dissociate completely to negative and positive ions. And if you look here, the purple will be the chlorine, and orange will be the hydronium ion. So this means that this is a strong acid, 100% dissociation in the water. On the other side, the weak acids. The weak acids are like this acid here, hydrofluoric acid. It's weak, and by weak we mean it's not 100% dissociated in water. So if you look here to the molecules, you can see 3 colors. You can see the HF, which is a purple color, and then you can see also the F, which is a green, and you can see the hydronium, which is H3O. So you can see that there are some molecules that didn't dissociate and still in the solution. And this is what we mean by weak acid. So it doesn't dissociate completely. And you can see here that it's reversible reaction. As long as dissociate, they get together and form again the acid. So when it's not dissociated, when the acid is not dissociated 100%, we call this a weak acid. Here is another table for the strength of the acids and the bases. Bases also have the same concept. If it's dissociating completely, then we have a strong base. If it's not, we have a weak base. Again, this is the same photo, strong and weak acid dissociation, and you can see the protic acid. The protic acid are those acids that donate 2 or more hydrogen. Like you can see H2CO3. We call it the protic acid. H2SO4, H3PO4. All of these are called the protic acid, and because they give more than one protic acid, because they give more than one hydrogen atom. So you can see if it dissociates in water, you can see it dissociate into hydronium and HCO3. And HCO3 is not stable. It dissociates back into 1H and CO3 negative ion. Same thing goes H2SO4. Dissociation in water, H3O, and then HSO4. HSO4 is not stable, and it dissociates back into another molecule of hydronium ion and SO4 polyatomic ion. Strong bases and weak bases, same idea. So strong bases, as the KOH here, dissociate into K and OH, K positive and OH negative. All the household products are considered strong bases. That's why they clean. The weak bases, like ammonium hydroxide, it dissociates. So the ammonium here dissociate in water to give NH4 and OH molecule, where few molecule of NH3 is also located in the solution or present in the solution. These are some examples of strong bases and a weak basis, and all of them are the cleaning stuff at home, basically, the cleaning products. Another topic is the direction of the reaction. So the direction of the reaction always go towards towards the strong acid. So strong acid have weak conjugate base that do not readily accept hydronium ion. As the strength of the acid decrease, the strength of its conjugate base increase. So let's see, what does this even mean? H2SO4 is a strong acid and it's dissociated in water. So if this is an acid, then the water will play in here a base and a strong base. And in the dissociation, you will see H3O and HSO4. Which one has more hydrogen? The one that will have more hydrogen at the beginning, it will be the acid or the conjugate acid, and this will be the conjugate base. So the strong acid here produce a weak acid. The strong base produce a weak base. Weak conjugate base. Direction of the reaction again. So CO3 plus H2O, again this is a weak acid. So if this is an acid, this will be the base. And which one has a hydrogen ion at the beginning? We have this, so this will be a stronger acid. It's stronger than this because it has more hydrogen here, and here we have a stronger base. As you can see, this table here can tell you if the acid is stronger base depending on the arrow. You look at the arrows and determine if it's a strong acid or strong base or weak acid or weak base. Identify the stronger acid in each of the following. So those two, you can check it in here and see that HNO2 will be stronger than H2S. HBr is stronger than H3O3. And yes, if we have a test, I will give you this table if I have a question about this. Dissociation constant. We explained the equilibrium constant before, if you remember. We used to say that the equilibrium constant, KC, equal to concentration of products to the power of its exponent, and divided by the concentration of reactants, also to the power of their coefficient. So this is the equilibrium constant. The acid, the acidic constant, or the Ka, is equal, same thing, products over to the power of the coefficient over reactants to the power of coefficient. And we call this the constant for the acid. If we're looking for constant for the base, it will be this way. Also same form. If we're looking for the constant of the water, it will also be the same. So we'll dissociate them and see how can we write down these constants, and of course how to calculate um, equations. So here is this equation. When this acid dissolves in the water, it dissociates into these two hydronium ion and this molecule. Let's try to write down the Ka, or the acid dissociation constant. Products, which are these two, and we don't have any coefficient, so those over the reactant, which is acid. The water is 1, so just don't write it. And you will get this number. Weak acid have a small Ka. Strong acid have large Ka. So for example, if I give you some acids and asked you if this is a strong or weak acid, and I didn't give you the table that we were just talking about, then you just go ahead and give you numbers, and you just go ahead calculate your acid dissociation constant. If it's a small number, then you will have a weak acid. If it's a big number, then you will have a strong acid. Same thing with the base. So this is another example of dissociation. Same thing. You put the product over reactant, and the water is considered as 1. So you will get this number. So this is the Kb. And here, write the acid dissociation constant expression of nitrous acid. So try to do this, pause the video, try to do this, and come back to check it. So here you can see HNO2, dissociation in water, and then we get the arrows. If we will, this is an acid, so it will give away hydrogen, so we can say that this will ionize into hydrogen and NO2, and then the NO2 will come out, and then the hydrogen will be received by the water from hydronium. And then you put your products over your reactant, and if I give you a number, you apply your number. For the water, it's the same thing. We will consider one molecule as an acid, the other molecule as a base, and then we do the ionization, and then you will get this. And to calculate it, it will be equal to, so when you calculate it, you will find that the H3 hydronium ion is equal to the concentration of the hydroxide ion is equal to 1 times 10 to the power of minus 7. Sorry. And this is under temperature 25 Celsius temperature. So now you have the water dissociation constant equal to, and this is a constant, doesn't change, equal to 1 times 10 to the power of minus 7. Again, remember 7 is the number, the neutral number on the pH meter or the pH scale. Here you go. So this is the dissociation of pure water where both are equal. So they are both equal to 1 times 10 to the power of minus 7. If the hydronium ion become higher than the hydroxide ion, then we have a basic solution. If the hydronium ion here is smaller than, if the hydronium ion bigger, then we have an acidic solution. And by bigger means bigger than 1.1 times 10 to the power of minus 7. So you can see here, same thing, the 3 of them, and This is a neutral, this is acidic, this is